Hi guys, let's take a look at Achieve Section 4.4, Problems 1 through 7. I love their Problem 1. They're going to give you some original function, and then they're going to ask you to list in order whether f of 1 is greater than or equal to f prime of 1, which is greater than or equal to f double prime of 1. Okay, so the problem that I looked at on Achieve had what looked like to be a negative quadratic function. This is the graph of negative x squared shifted to the right and up. Now, I can clearly see that f of 1 is 0 on my graph. So I can say, okay, that gives me my starting point. Now, what would the derivative f prime of 1 be? I already know it's positive. How do I know it's positive? Well, look at the slope at 1. There is a positive slope on this function at 1. So I already know f prime of 1 is positive. Now, let's go ahead and graph out what the first derivative would look like. We know that anywhere where the original function is increasing, the first derivative is positive. And I also know that the derivative of any quadratic function, second degree function, is going to be a linear function, a first degree function. So this is like a negative x squared. Its derivative would be like a negative 2x. So I can say the graph of f prime of x is going to be some shifting of negative 2x where I know that the x-intercept has to occur at, now it doesn't specifically list this out, but it looks like this function flattens out at approximately 2. It's about twice the distance of where 1 is. So I know that somewhere to the right of 1, the derivative of f of x is going to hit an x-intercept, and I know at 1 it's going to be a positive slope because my function is increasing here. So I'll go ahead and draw in my derivative. It's negative 2x. That's probably been shifted up maybe 2 units or something because I believe its x-intercept is approximately 2. But now, no matter what, I don't have to get a specific graph of the function. I am 100% certain that the derivative evaluated at 1 is a positive number because the slope of this function is positive. And I know that that derivative has a slope of negative 2. Now, because I know that the derivative has a slope of negative 2, that means that the second derivative is just a constant function. Any linear function has a constant slope. This constant slope is a negative 2. So I know that f double prime of x, f double prime of 1, same thing as every other value of x on the second derivative, it's always negative 2. So now, the way that they listed the problems in mine, and sometimes they'll ask which is the largest, sometimes they'll ask which is the smallest. My problem was asking which is the smallest. Clearly in this case, f double prime of 1 is my smallest because it would be a negative 2. And that's going to be smaller than the original function at 1 because that's going to be 0. And then that's going to be smaller than the first derivative at 1 because that's going to be some positive value. So that my correct answer in this case would be f double prime of 1 less than f of 1 less than f prime of 1. Excellent question. Excellent question. Now, the next one is giving you a graph, and the graph it gave me on mine was it said assume a profit function looks something like this. And what I'm supposed to immediately see based upon that is that, well, if this is a profit function, then clearly the profits are going downward. And the fact that the concavity, this is part of an N, it's concave down, not only is the profits decreasing, but they're decreasing at a rapider pace as time goes on. So this question would have, or this graph, if this is representing a profit functions, I would say, well, you're losing money because your profits are going down and the situation's just getting worse because of the concavity interval there. Now, for number 3, it has us do our second derivative test. It will give you a cubic function here. Mine was 6x cubed minus 11x squared plus 7. I take the derivative of that to get to 18x to the second minus 22x. Second derivative, they didn't ask anything about critical points, so I didn't have to set the first derivative equal to 0. Second derivative, I get my 36x minus 22. Now when I set that equal to 0 to find the potential inflection points, I can see, well, that's just going to give me 36x is 22, x is 22 over 36, which I then went in ahead and reduced it to 11 over 18. Now the second derivative test is asking you to look at the domain of your original function, which is all real numbers, break it up with that potential inflection point. The only place where this graph could possibly change concavity is at 11 over 18. So I'll look at the concavity from negative infinity to 11 over 18 and from 11 over 18 to positive infinity here. I'm choosing test points in each of these regions. 0 is in my first region. 1 is clearly in my second region. Now, when I choose those test points, I plug them into the second derivative here. That second derivative was 36x minus 22. I know when I allow x to be 0 here, I'll just get a negative 22. What does that tell you? Well, it tells you that your original function is concave down. Whenever your second derivative is negative, the original function is concave down. It's going to be n-shaped. Now, when I plug in the 1, I would get 36 minus 22, positive 14. The only thing I care about is that whenever the second derivative is positive, the original function is concave up. So now we have our intervals of concavity, when it's concave up, when it's concave down. And then, in this case, it's going to want you to find the point of inflection. So it wants you to find the coordinates x, y. So after you find out that yes, 11 over 18 is the location of the x value of the point of inflection, you then have to go back in and find the y value by plugging 11 over 18 back into your function. Now, when I did that, I just went into my calculator and said, well, let's store 11 over 18. I hit store that in for x. And then I typed in my function 6x raised to the third minus 11x squared plus 7. And then you'll see, yeah, I get that. Math enter. They wanted an exact fractional value, so 2071 over 486 there. Pretty nice problem. Now, number 4 here, as I'm working to, try to make that a little bit more clear. Here we go. Number 4 gives us a 5th degree function. Say, well, okay, it's going to be very similar to the last one. Again, I'll take the derivative twice. Power rule each time. I'll get 40x to the 4th minus 20x to the 3rd. No need to find critical points, so I just keep on going. 60x cubed is my second derivative for the first term, then minus 60x squared, the second derivative for the second term. We set this equal to 0 to find our potential inflection points, and when I do that, I can say, well, I could easily factor out a 20x squared out of that group. When I do, my first term is going to have an 8x remaining. My second term only has the 3. So now my potential inflection points will be when 20x squared is equal to 0. That's true when x is 0. And when 8x minus 3 is 0. That's going to be true when 8x is equal to 3 or x is equal to 3 over 8. So now I get my 2 potential inflection points. I need to find out if they're actual inflection points. So I set up my second derivative test. I'll go from negative infinity to 0, from 0 to 3 over 8, and from 3 over 8 to infinity. That's just breaking up the domain of the original function with these potential inflection points. We choose test points in each region. A negative 1 represents the first region. I'm choosing a 1/8 to represent the second region, and a 1 to represent the third. Now, what are we doing with these test points? We will plug them into the second derivative, and all I care about is the sign of the second derivative. So the first thing I did is I just went ahead and showed that first sign is always positive. 20x squared, I don't care what you evaluated it at, it's always going to be a positive factor. So that tells me that the only factor that's going to determine the sign of my second derivative is this second factor. When I plug a negative 1 in, I'll get negative 11. Positive times a negative is a negative there. I know my function's concave down in this region. When I plug a 1/8 in, 8 times 1 over 8, that's going to give me 1. 1 minus 3 is still a negative 2. Positive times a negative, still a negative. I would get a concave down in this region. When I plug in the 1, I can see that that last factor would be a positive 5. So then I can see, well, since that last factor is a positive 5, both factors are positive. My second derivative would be positive, and my function would be concave up in that region. So now I can say, okay, The potential inflection points were at 0 and 3 over 8. This shows you there is not an inflection point at 0. So the graph is going to be concave down before 0, and the graph will be concave down after 0, but not at 0. So you would need to put negative infinity to 0 union 0 to 3 over 8 for the intervals that are concave down. And then for the intervals that are concave up, you would just say, well, it's going to be from 3 over 8 to infinity. In this case, it just asks for the x location of the inflection point, which is what I would prefer them always to ask, and it's 3 over 8. Okay, up next, when I look at number 5, we've went from number 3 had a cubic, number 4 had a 5th degree, number 5 has a 4th degree. So it's still just asking about the intervals of concavity. So I'm going into this function 13x squared plus x to the 4th. I take the first derivative, 26x plus 4x cubed. Second derivative, I'll get 26 plus 12x to the second. Now, what you're instantly supposed to see there is, okay, you've got a positive number plus 12x squared is guaranteed to be positive or at least 0. So 26 plus some non-negative number, it can never equal 0. Now, if you tried to solve out for x, you'd only get imaginary solutions. Well, what does that tell you? There's no real number where this function can ever equal 0. So, in other words, f double prime of x is always at least 26, so it's always positive. That tells you that your original function is always concave up. So what interval is this function concave up on? From negative infinity to infinity. When is it concave down? Never. And again, that's because your second derivative is positive. I went ahead and said here we know that the second derivative is always greater than or equal to 26, but the only thing we need is that it's positive there. Anytime the second derivative is positive, the original function is concave up. Number 6, hopefully it's a little more interesting. We have x times the group, x minus 9 on the root of x. And just to make the derivatives easier, I went ahead and distributed that x throughout the group, x squared minus 9x to the 3 over 2. The problem gave us that x had to strictly be greater than 0. Okay. Now, I take the first derivative. I'll get 2x. 3 over 2 comes down, multiplies the 9 to give me 27 over 2, x to the 1/2. I take the second derivative to find my potential inflection points. I'll get 2 for the first term. The second term, 1/2 times 27 over 2 will give me 27 over 4, and then x to the negative 1/2 power. Now, I need to set this second derivative equal to 0 to find my potential inflection points. From this step to this step, I went ahead and said, well, x to the negative 1/2, all that means is the square root of x in the denominator. So I have 2 minus 27 over 4 on the root of x is equal to 0. When I try to solve, I'm going to go ahead and move that 27 over 4 root of x to the right-hand side, and it becomes positive. Then I cross multiply, or you could just say multiply by 4 on the root of x on both sides. That gives me 8 root of x equals 27. From this step to this step, I simply squared both sides. 8 on the root of x squared is 64x. 27 squared is 729. So x is going to equal 729 divided by 64. Okay, now that's my only potential inflection point. So I break up the domain of the original function, which they told me had to start to the right of 0. So I'll say, well, my first test interval is going to go from 0 to my potential inflection point. My second one's going to go from that potential inflection point to positive infinity. I chose a number between 0 and 729 over 64. I know 1's inside of there. And then some number between here and infinity. I know 64. Sorry, I know 20 is, although 64 would be as well. So nothing special about those 2 points other than they are inside of the interval that they're supposed to represent. So now I'm plugging these test points into my second derivative, which was right here. When I plug a 1 in, I'd get 2 minus 27 divided by 4. That's going to give me 2 minus 6.25. That's going to be a negative. All I need is the negative. I don't need the specific number, because everywhere the second derivative is negative, my original function is concave down. When I plug a 20 in, that 2 minus 27 over 4 on the root of 20, that denominator is going to be so large that it makes that 27 divided by that number small, and I'll have 2 minus a number smaller than 2. It's going to stay positive. Now again, I don't care about the specific number. All I care about is that it is positive. Because anywhere where the second derivative is positive, my original function is concave up. So now to answer this question, you'd say, yes, your potential inflection point is an actual inflection point. We have a point of inflection located at x equals 729 over 64. Our function is concave down from 0 to that point, and our function is concave up from that point to infinity. Pretty nice. Number 7 continues the original problems where we have a product given in the beginning. Just like I did last time where I distributed the x through, I would recommend going ahead and doing the algebra first in this problem too. It makes the calculus easier. So the first thing I did here is I FOILed out these two binomials, x minus 10 times 1 minus x cubed, to get x minus x to the fourth minus 10 and then plus 10x cubed. I went ahead and rewrote that in descending order. Negative x to the fourth plus 10x cubed plus x minus 10. And now that I have it written like that, I can go ahead and start taking my derivative. First derivative, negative 4x cubed plus 30x squared plus 1. From here to the second derivative, again, just power rule, these are easy derivatives. We get negative 12x to the second plus 60x. Of course, 1 became a 0. I set this equal to 0 to find my potential inflection points. So now, when I do that, I can factor the left-hand side. I factored out a negative 12x. When I do that, that left the first term to be a positive x, and the last term, 60 divided by negative 12, left me a minus 5. So now we set these two factors equal to 0. This says, well, you're going to have a potential inflection point at 0 and at 5. So now, if those are my two potential inflection points, I'll go ahead and do my second derivative test and go from negative infinity up to the first inflection point, 0. Go from that first inflection point, 0, to the second, 5, and then go from 5 to infinity. I chose negative 1 to represent the first region, 1 the second, and 10 the third. I'm plugging those test points into my factored second derivative. I already know that when I plug a negative 1 in, negative 12x is going to be positive. X minus 5 is going to be negative. It would be a negative 6. A positive times a negative is a negative. I know my function's concave down in that region. Now, when I plug in a 1, my first factor is positive. Negative 12 times 1. My first factor is a negative. My second factor, 1 minus 5, is a negative, but we know the product of two negatives is a positive. Thus, the second derivative is positive, which means our original function is concave up. Now, when I plug in a 10 to represent the last region, once again, I can see that first factor, negative 12 times 10, is a negative. But my second factor now is positive. I'd get 10 minus 5 is a positive 5. Negative times a positive is a negative. Anytime the second derivative is negative, your original function is concave down. So now we can see that each potential inflection point was a legitimate inflection point. It changed concavity from concave down to concave up at 0, and it changed concavity from concave up to concave down at 5. So your problem will be asking a couple of different things. Intervals of concavity. This function is concave down from negative infinity to 0, union 5 to infinity. It's concave up from 0 to 5. Now, this is another one of those problems where it's going to ask the points of inflection, meaning it wants the x and y coordinates. So then all you have to do is you need to take each of these inflection or x values of inflection points, plug them into the original function to get the y value. So if x is 0, we can easily see, hey, the y value would be negative 10 here. So I'll have the ordered pair 0, negative 10 is one inflection point. And then when you plug a 5 in, and what I did is I figured out it'd be easier to plug a 5 into the original expression. I'll get negative 5 times, it'd be 5 minus 125, 1 minus 125. I'm getting negative 5 times negative 124 for 620. So the ordered pair of that inflection point when x is 5 is the ordered pair of 5, 620. Hope that helps you out with these first 7 problems. Let me know if you have any questions. I'll be glad to help.